All right, everybody, we're back for another video by popular request. So today we're just going to be doing mechanism, reactions, and then two synthesis that somebody sent in the group me, and then that should be good for your exam. So let's just get started with the mech. So it says propose a reasonable mechanism for this transformation shown below using curved arrows to indicate the flow of electrons. You do not need to draw the transition states and do not add anything. Okay. So generally the best way to approach these problems, let's go a little thinner here, sorry. The best way to approach these problems is look at what changed in your final product compared to your initial, right? So let's highlight some things. We have this cyclopentane group, right, with this carbonyl coming off. And that is the exact same. So we know we're not going to react that side at all, right? Let's just do a different color. Now we have this cyclohexane, right? And we see for the most part, it remains a cyclohexane, right? So we're not going to react that. Then the last thing we look at is the left side, and we notice that we have carbonyl that turned to an alcohol. So this is like something is going on here. Let's circle this. And then additionally, we see this CH3 is moved. So it was on the left before, it was on the left, and somehow now it's on the, sorry, it was on the right, now it's on the left. And then the last thing we notice is when we look at the double bonds, this thing went from a benzene ring, right? This was a benzene here. I'm so sorry. It went to a benzene. So this is like di-substituted alkene here. And then it became a benzene. So let's just follow our mechanism one by one. So the first thing and the most, or the easiest first step for you to follow would be to recognize that, okay, my O double bond turned to an alcohol. So how do I do that? Well, in the presence of an acid, right, H plus acidic protons, how this works is the H plus, it's attacked by the carbonyl. So let's draw that out. And this structure looks something like this. Okay, so now notice that our O is bonded to three things, right? And it has a lone pair left. So we used one of these lone pairs to attract the H, and the other one stayed there. So if we do counting, we can see 1, 2, 3, 4, 5 valence electrons. Oxygen 1, 6. So 6 minus 5 equals plus 1, right? So this oxygen has a plus charge, okay? So then you need to look at your product, right? And recognize that, okay, not only is my oxygen not have a plus charge, it's also not on a double bond. So this is where you kind of have to recognize that the only way to get rid of that plus charge would be to kick that double bond onto the oxygen. So if we were to kick this bond here, right, then we would get a structure that looks something like this. What will it look like? This. And then notice these red electrons, they came from this double bond, right? So hopefully that's all making sense right now, right? And then now look at where your positive charge is. So now your positive charge, since this carbon used to be engaging in a double bond, and now it's a single bond, that lost basically an electron pair, so it's plus charged. Oh, and we're also forgetting the CH3 actually. Let me move back some steps. So this CH3 is here, right? Hopefully you recognize that. Okay, and that's going to be important in this step. But basically now what's going to happen is, let's look in our product, right? So in our product, we see we have a benzene ring, right? So we know somehow we're going to add a double bond we're going to add a double bond between this and this. Do you see how the product has a third double bond, whereas the one on the left doesn't? So that's an indication that we're going to do some kind of elimination reaction, basically, later on. But if we go step by step, right, what we can do is, now that we know we have a plus charge here, right, we can move our double bond down here to move that plus charge here. Because we know in our product, the double bond needs to be here, right? There is a double bond here and here. Whereas over here, it's up here and here. So move this top one to the left. So the best thing would be to move this here, like this, and that would give you this. So you'd be a step closer to your final product, right? So let's draw what that would look like. So we're gonna kick this. This is a little unclear, but we're gonna move this double bond from here to this wall, okay? So let's just draw what that looks like now. It's gonna look something like this. Right, and then okay, and then recognize that the plus charge moved again. So if this carbon was plus and it gained a bond, right, it's no longer plus. This carbon is still engaged in the double bond, right? But between these two structures, this carbon now lost a double bond, right? So what does that mean? That means that this is going to be plus charge, okay? And this sets you up for the next step, because if you look in your product, right? Let's take a look back here in our product. The methyl group actually ends up where this plus charge is. So the next step that you should take is to just move this methyl group to here. And we call this what? Very good, it's an alkyl shift. Okay, so let's draw this real quick. Oops. Shift this here. Okay, so now we need to look at our product again and recognize what is missing, right? So between this and this, I'm forgetting something, right? Since I did an alkyl shift here and this was plus, now the plus has to be here, right? Let's put a plus charge here. Okay, and now this is where you need to recognize something kind of tricky, that there's an invisible hydrogen on this carbon, okay? So if we look at our structure at the bottom right here, this, right? And then we look at this, we see that everything is the same. This is the same. This thing is the exact same. This are the same. This is the same. But if you notice, this double bond here, this double bond right there is not right here, right? So we need to form a double bond somehow. And so the way you show that is via elimination. So you don't have to write elimination here, but for you guys to know, elimination reaction, you can just use any base with protons and then eliminate the hydrogen and kick down that. And what that will do after a series of steps will get you to this. Okay, so that's the mechanism problem for today. And then if you have questions, just shoot them in the group. Okay, next up, we have this reactions page. Let's see what it says. So write the products of the reactions shown in the center, blah, 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 blah. This is important. Make sure to include stereochemistry. Okay, but don't write mechanisms. Obviously, you don't need to show arrows. in the two reactions where both the conditions and the product are missing, write in any correct reaction. So this is kind of interesting. He wants you to make your own reactions here and then put it in the box. So you kind of have some free will on this side. Whereas here, obviously, you have reagents that you need to know, right? So what else did it say? Don't let the bicyclic structure intimidate you. Yeah, that's actually how kind of him to say that, right? Don't let it intimidate you. Okay, so we'll just get started with this. Should we go left or down? Let's go left and knock this side out. So the first thing to recognize is you have an alcohol, right? This is an alcohol, OH, alcohol. And when you react with acids and heat, you should know that this reagent, any acid in heat, I'll write this out so you guys can look at it later. Let's make this something like, okay, so acids in heat make alkene via elimination reaction. Okay, and not just any acid, by the way. Make sure it's a strong acid. So that could be like H2SO4, H2PO4, question mark? Yeah, it should be okay. Yeah, and then obviously H plus is a very strong acid because it's a positively charged proton. So then you're probably asking, okay, does it form an alkene, you know, up here or down here, right? And that would be a very good question. So to answer that question, draw in the invisible hydrogens, right? So the invisible hydrogen here is on a wedge. Here, it's on a dash. And now I want you to tell me, for elimination, the hydrogens must be what? Think for a second. Must be anti-periplanar. So all that means is the leaving group, the OH, must be anti to the proton, okay? So that's why we don't eliminate in this direction, because they're both on a wedge. Hopefully that makes sense. They have to be anti. One on a wedge, one on a dash, okay? So we eliminate on the bottom left side to make a more subalkene. And then if you're wondering why we didn't eliminate on this side, like here, right? This would make a 3' alkene because it would be attached to 1, 2, 3 things, right? But on this side, if we do it, it'd be attached to 1, 2, 3, 4. So this is more sub. So that's why we go left, okay? Anyways, let's do that. And so our product is going to look like this, right? This methyl group. Well, let's first put our double bond, right? So this is going to stay on a dash. Then this loses stereochemistry because on a double bond, there's no wedges and dashes. Everything is linear at 180 degrees, I'm pretty sure. So that's the product for that, right? And then we can move up. Everybody should know HBr in peroxide. This is a peroxide. Let's do it in pink as well. Peroxide. Why is it doing that so much? Stop. Okay. Peroxide with HBr. What does that do? This adds bromine anti-mark. Okay. So let's just draw what that will do. Basically, it reacts with the alkene, right? So all the alkane parts stay the same like this, right? This methyl will stay here. And now you're in a unique position because this position is tertiary substituted, right? This carbon, let's see. This carbon is bonded to 1, 2, 3 things, right? Then you look at this carbon. This is also bonded to 1, 2, 3 things. So technically, in this case, you can add the bromine to either side. They're both acceptable, okay? But I'll just add it on the left side because I'm left-handed, but yeah. Okay, now we can go down to O3, then this dimethyl sulfate. So this is the same thing as DMSO if you're confused or worried. Yeah, so ozonolysis of alkene yields 2 ketones, basically. So the easiest way to do this is to look at our alkene, right? And just draw a squiggly line through the alkene. And then just put O's. Oh my goodness. Put O's on both sides of that, okay? So what I mean by that is we drew that squiggly... Oh my goodness. Anyways, we drew that squiggly line, right? So everything else stayed the same, right? This all is the same, chilling. Actually, I made a mistake. Let's go back. This all stayed the same. Oh my god. And then the alkene, just, it's too small for you to see. Let me draw it bigger. Let's draw it a little larger. Basically, wherever the alkene was, split it and put double bond O on both sides like that, right? Like this. Like that. So all it does is it cuts the double bond in half, right? And it adds 2 double bond O's, right? So we split it here and then just put a double bond O here and a double bond O here. And then make sure you leave a gap because they're technically not connected, okay? So that's the left side done. Now onto the right side. We'll do this bottom one first real quick. So this is an interesting reagent. I don't know if you know the mechanism for this, but basically what Na does, this Na, it basically acts as Na minus, right? That's what it acts like. Okay, don't treat it like that, but this is just for your understanding. And it deprotonates, basically this, and it makes this structure into this alcohol, ONA, and the O is plus, and the Na is minus, if that makes sense. Wait, no, I'm sorry. The O is minus, and the Na becomes plus, okay? So basically, it replaces the H with an Na plus counter ion, okay? So now you have O minus, basically, treat it like O minus, and then O minus, when it reacts with CH3 bonded to I, hopefully you recognize that I is a good leaving group, right? So all that's gonna happen is O, let's do a different color, sorry. O is gonna attack CH3 like this and kick off the I. So simply the product will be this, like this is the same, this is the same, this is also the same, right? This is the same, this thing is the same. And this O stayed here and it now bonded to CH3. And that's it for those, okay? So now we have 2 boxes where we can do whatever we want. And I would say just do like anything you remember. Obviously what I'm gonna write down right here is not like a definitive answer. There's like hundreds of reactions you can do. But what I would say is you can use different reagents, right, to pretty much do a bunch of things. So one thing I'll say is you can use, on this structure, you can use terbutoxide. That's the first thing I would think of, which is this big bulky base. And that makes less subalkene. So that'll actually make, what will that make? This, like this. That'll be there. And then it'll make an alkene there, okay? So you see on the left side we made a more subalkene. Now we just made a less sub. So technically it's not duplicating the reaction, right? And then if you want, you can use different reagents here. But I mean, there's only so much you can actually do here. Maybe you can use like 1NaOH, right? To deprotonate this alcohol. And then you can do, like, you can add this thing. And so all that will do is deprotonate the alcohol, right? So we'll be dealing with O minus. So this will deprotonate. The NaOH is gonna, let's draw this out for you. The NaOH is gonna grab the H, kick it onto the O, make O minus. O minus is then gonna attack here and kick off the bromine. That's like SN2. So then the product will be like this. Same, like this. This O will be here, and then it'll just be like attached to 2 carbons, basically. Yeah, and that'll be that. Oh, and don't forget this, obviously. Okay, so that's pretty much how you do the reaction section. If you have questions about any reagents that I used, you can shoot them in the GroupMe, okay? And then the last thing we're gonna do today real quick is 2 synthesis that people sent in the GroupMe. So this one is a little bit trickier, right? This is like, oh, the instructions are like synthesize from, given materials, right? Okay. And then it's the same thing down here. Given this, synthesize this, okay? So I think the second one is actually easier, so we'll go ahead and do this first. But recognize that you have a carboxylic acid, okay? So immediately in your mind, you need to be thinking, how do I make carboxylic acids, right? What are the reagents you know? So this is where the knowledge of your reagents comes in handy. You know a few that can make carboxylic acids, but let's write them out. So on a primary alcohol, you know that K, well, let's write it all out, I'm sorry. Primary OH, you know that KMnO4 with OH, 2H plus, this makes carboxylic acid. And then another one, you can also use chromate if you know that reagent, like Na2. I'm trying to think of what it is. Yeah, I think it's Na2CrO7. It's the Jones oxidizer basically, but you can also use this Jones oxidizer, which is like Na2CrO7 basically. Let me double check the Jones oxidation. I don't want to give you the wrong thing. Okay, actually, it's not the Na2 version, right? Jones oxidizer is actually the normal version, CrO3 with H2SO4. So both of these reactions on a primary alcohol will give you carboxylic acids. So let's just work back to a primary alcohol, right? Primary alcohols look like this. And then we know if we hit this with KMnO4, and make sure you write this out like this, stepwise, OH minus, and second step, H plus, that'll make the carboxylic acid, right? And then just look at this thing here and ask yourself, how do I get from there to there? And the difference you'll see is, this is a bromine, this is an alcohol. So what are some ways we can swap bromines for alcohols, right? So let's first draw what we are going back to. We're gonna go back to a bromine, basically. Bromine, right? So think to yourself real quick, how can I swap a bromine with an OH, right? And what do you guys think? If you said NaOH, right? This will act by SN2, like this NaOH will come here, and this will get kicked off here, and that'll give you this. So this is how you do the synthesis, basically. Yeah, hopefully that makes sense. And then the last one we're going to do for today is this synthesis here. And this one is a lot trickier than you would expect. Because as you guys were saying in the GroupMe, this thing does lose a carbon, right? This is 1 carbon. Let's draw this out clearly. This is one carbon here, 2 carbons here, and then this is just 1, right? So we lost a carbon. So now you need to think to yourself, what are the reagents I know that make ketones, right? And also involve the loss of carbons. And if you don't know that one, then this one might be a little tricky because there's no way around that. So you need to recognize that to make a ketone, right? I can do a few things. I can, if I had an alcohol here like this, I could do PCC, right? But the only issue is I can't get an alcohol here on the ring. The alcohol would end up here. Like if we did NaOH, this would attack here and go here. So this wouldn't be on the ring. You see how it has to be on the ring? So this reaction won't actually yield the proper answer. So then you have to ask yourself, what other reagents do I know make a double bond O, right? And think back to the last unit. Hopefully when I show you this, it's clear. But if I have an alkene, right? If I have an alkene like this, what do you guys think I can use to make a ketone? Just think for a second, right? And the reagent that does this is O3 with ZnHCl. And this is the ozonolysis. So this actually will, like we did in the reaction section, right? It'll split the alkene. It'll split the alkene here, and then you'll get 2 dope 1-Os, right? So that's why this one is so hard, because you need to recognize that it's not simply using an alcohol. It's using an alkene and ozonolysis, right? And then from here, we know we need to go back somehow to this bromine structure, right? So let's just draw this out here like this. This. All right, and recognize that we added what? We added a double bond, right? So we lost the bromine, we added a double bond. So what kind of reaction is this, right? It's an elimination reaction. Elimination reaction forming alkene, right? And then you can use any elimination reagents, you know, any strong bases like NaOCH3 that we used yesterday. And also I forgot to mention, if you want to really emphasize that elimination is happening, put this triangle, and what this means is heat, because heat favors E1/E2. So it'll indicate that elimination is happening more strongly, but it shouldn't be a big issue, but I would just recommend adding that. Alternatively, you can use, you know, the other elimination reagent, you know, terbutoxide with a K+ counter ion. Because in this case, it doesn't matter if we make a less sub or a more sub alkene, because there's only one place that protons can be pulled from. The proton has to be pulled from here because the leaving group is here. So how this will work is we have H here, right? So this base will grab the proton, kick this here, and kick this off. And that just so happens to be the allowed starting material, right? So this guy is the same as this. So you're done, okay? And I think that's it. Yeah, I would say the hardest problem we did today is this, right? So if you're confused on this, definitely let me know and we can go over this. But let's just grade this real quick, right? 50, like 60. I'll give you guys 50 for this one too. And then let's give you like 1,000,000 for this. All right. Yeah, that's pretty much it. So yeah, if you have questions, just shoot them in the GroupMe, and then thank you for watching.